So all we're talking about today are the limits at infinity. So this means that your x values are approaching infinity. So in that case, we're going to be looking from blue for the limit as x is approaching positive and negative infinity. So what that results means is that we're talking really about the end behavior of the graph. So what is your graph doing as x, at the far right arrow and the far left arrow? Are there certain values that it's approaching, or is it really just going towards infinity or negative infinity itself? All right, so we have this graph here. And if we were looking at this, so your function is x plus 1 over 2x. Zoom in a little bit. And if we were using limit notation for this, we can see that it has this horizontal asymptote at 1/2, at this y equals 1/2. So what we would say for limit notation on this is that as x is approaching negative infinity, our limit is 1/2. Our y value is approaching that horizontal asymptote at 1/2. And as x approaches positive infinity, our y value is also approaching 1/2. So it's possible that your limits as you're approaching negative infinity could be different than the limit as you're approaching positive infinity. Because let's say that you had a graph that looked like this. Right, so if we had a graph that looked like that, so if we had this graph that looked like this, if we're looking at x approaching negative infinity, which would be this side right here, we would say then that the limit as x approaches negative infinity of this function would be 0, since our y values are going towards that horizontal x-axis. But then this other part right here, this end of our graph, right, because you're going to have those two ends, the limit as x is approaching positive infinity of our function, we would say is actually infinity, because we're really describing the end behavior. What is it going towards? All right. So the limits mean that you get really, really close to these horizontal asymptotes, but you don't necessarily have to cross them or touch them. Because again, remember that idea of a limit is that you're just getting potentially really close to that value. So for end behavior limits for these positive and negative infinities, you'll either be approaching some sort of constant, or you could potentially be approaching that positive or negative infinity. Okay, so they're going to be numbers, or we're going to be talking about them as positive or negative infinity. The next thing we have to look at is, without a graph, we can actually just use our function to determine what the end behavior is going to be. So if your function, if you end up with a higher degree in the denominator, so if your denominator has a higher degree when you're in standard form, the limit as x approaches positive or negative infinity will equal 0. And the idea behind that is, if we were to look at this equation right here, that 1 over x to the r, if we were to plug an infinity in for the x, and if you end up with 1 over infinity, so 1 over some infinitely large number is actually like a really small number. So that's why we say when we end up with that 1 over infinity, it will get really, really close to 0. So if we needed to find this limit, The first thing you look at is, okay, we have an infinity, which means we need to decide what the degrees of those numerators and denominators are, and we need to be in standard form. So your first step is to put your function in standard form. Right, in the numerator and in your denominator. So in this case, the fact that we have these two terms, we have to combine these into a single fraction. And so in order to combine these into a single fraction, we need a common denominator. So we're going to put 4 over x squared, but then that means we also have to add that x squared into our numerator. So this is, we're going to say, is 4x squared minus 3 over x squared. So now once you're in standard form and we confirm that our limit is approaching infinity or negative infinity, so we're looking at the end behavior, then what we're going to do is we're going to compare the first term of the numerator with the first term of the denominator and see what that simplifies down to. So the end behavior of this whole function will be the same as the end behavior of whatever 4x squared over x squared is. And 4x squared over x squared is just 4. And 4 is a horizontal line, right? So the limit of a horizontal line is just whatever the value of your horizontal line is. So the limit of this original function at its end, so this means it's approaching a horizontal asymptote at 4 as x approaches positive infinity. So this is really what we just talked about with the idea that you're comparing those first terms whenever you have that rational function. And then the other thing is that the limit of a function as x approaches positive or negative infinity here with this piecewise function is that, again, you're just really comparing those first terms when we're in the same term. So that a sub n and a sub m means that they would have to be that same term. So if we wanted to find these limits at infinity, okay, so in part A, so if we're looking at A, we would say the limit as x approaches infinity. If this is our function here to start for A, first your thought is it in standard form? Yeah. So the limit as x approaches infinity is going to be the same as if we were just comparing the first term. So it will be the same as negative 2x over 3x squared. And if we were to simplify that, we would have the limit as x approaches infinity of negative 2 over 3x. And so if you were to plug an infinity in for x, you would get negative 2 over 3 times infinity, which means your denominator is getting infinitely large, which ends up giving you 0. So that horizontal x-axis is what the limit of this function is. All right, the next one, if we looked at this for part B, and we had the limit as x approaches infinity, and again, we're in standard form, so now we're comparing negative 2x squared over 3x squared. So when those degrees are the same, those x squareds would simplify. So we're really looking at the limit of negative 2/3, which whenever you have a constant, your limit is just that constant. All right, so for part B, our limit would be negative 2/3. And then for part C, if we're finding the limit, we're comparing negative 2x cubed over 3x squared, which is giving us the limit of negative 2x over 3. So when you end up with that x in your numerator, you get negative 2 times infinity over 3. Your numerator is infinitely large, but look at, we have a negative, so this is actually going to go towards negative infinity.